then allow me to introduce the next keynote session for you. The session that will end this day. With a big smiling face, I'm introducing to you the Hugging Face team. And we will have the co-founder of Hugging Face on stage, Thomas Wolff. And he's not alone, he brought his team, his Amsterdam-based team actually. So that's really great. And while I think they don't really need an introduction, let me give a few words. I think when we were selecting keynote speakers, we're looking for very relevant topics and inspiring people, right? And they will be talking about training large language models. Well, undeniably relevant at this point. As organizers, we even needed to make sure not to create a conference about LLMs. This is how many proposals we got. And everyone is talking about the Hugging Face tools that they use for their projects. And inspiring, I mean, Hugging Face is open sourcing the Transformers and Datasets that we can all use here. And we have the co-founder or the initiator on stage here, so pretty inspiring to me. Happy to have you all. Please welcome to the stage Thomas and Julien, Guilherme, and Alessandro.
Just stand around.
Can you hear me? Yeah? Okay, great. Well, I'm very honored to be here. Thanks a lot, Sophie, for the introduction. Very happy to be here with the team, Julien, Alessandro, Guilherme. So if you've been following a bit the news in the AI world, I mean the research news, you probably saw there was a new Falcon model. That's the new biggest open source model. So they are the one who trained this model. Props to them, congratulations. And actually, I decided that because we are in Amsterdam, and they are there, we actually talk about that. So you will have actually a presentation on what is maybe the hottest model today, or at least last week was the hottest model. And we'll split the presentation in two. I'll first present the whole Hugging Face ecosystem with a very wide overview, and then we'll do this very researchy focus aspect. So let's get started. I start with a little bit of history to tell you why we're here today, why we're talking about AI. So I think it started about 12 years ago, if we have to start it, when software started to eat the world, the famous sentence by Anderson Horowitz, which has proven very true, I would say. And that was the first, I would say, huge technology shift brought by high tech, right? The second one started kind of maybe less visible in the beginning. 2017, we started to have deep learning that was working. For the first time, like neural network were actually getting better than all the technologies, right? And we had this very visionary post by Cappelli saying that deep learning was going to eat software and bring a software 2.0, where we would not program stuff, but we would just put data in a black box. Well, it was just only the second phase of eating, because now, last year, I would say transformers have started to eat deep learning. So what are transformers? They are this very versatile architecture that can be applied to actually any type of data, almost. Well, there was probably at PyData a lot of discussion around is it working in all cases? In many cases, it's also still not working. But definitely, transformers are what is powering ChatGPT. They are also what is powering now, like the sound generation things, and like basically a lot of things is getting focused on this architecture. And much more closest to us, I would say, is now the advance of what people are calling generative AI, which is basically the realization of this idea that we just put data in a model and we'll see what it gives, and it's actually giving very interesting things. Now, generative AI is hungry. That sounds dangerous. And we are, I think, are today at maybe a key point in history of ML and machine learning. Well, there is a couple of things. One thing is that for the first time, well, I guess here a lot of people are software engineers, but for the first time, this technology is now being used mostly by people who are not software engineers or ML engineers. Well, just a few years, or maybe I would maybe dare to say just 1 year ago, it was mostly a subset of software engineers, like people who knew both how to code and also how to train model that was using them. And today, basically, anyone, my mother is asking me questions about ChatGPT, and she's not a software engineer. So there is this huge turning point. And we're also at a crossroads, specifically for Hugging Face, I would say, but also here for PyData, which is, I think, the home of open source software, right? And we have a choice now between two futures. We can say this new software, these new models, they're actually just an extension of software, and they should also be open source, right? They should also be open, and that would be better for everyone because everyone can contribute. All of you could help develop model. But there's a lot of other people who think maybe they should not be open source. Maybe there should be here a stop where software might be open source, but ML model, this software 2.0, should not be open source. These are a huge debate. Also internally at Hugging Face. So Hugging Face, I'll show you, we are, I would say, maybe a little bit like neutral platform here. So for instance, we host a lot of open source model on the hub, but little people know that actually the majority of the model on the hub are private. Like 2/3 of the model on the hub are private. So we kind of see both sides. And I would say both sides have advantages and drawbacks. I kind of summarized a couple of them here, well, the most salient, right? If we go to a future where we closely control every model, it might be better for security, for risk. People are talking a lot about misuse of model, right? Like adapting model. People are also talking a lot about model getting rogue, so Terminator-like thing. I personally don't really believe in that, but and I would say it's maybe even a matter of believing or not. Sometimes it's almost a cult. But yeah, there's definitely some question. And one question is also the business model, right? If you give everything for free, if you train model and give them for free, how do you make money? So that's a big question. Another thing is, let's say, okay, we have no problem with business model, we're not scared about these models, and we look at open source. Then I think there's a lot of interesting thing, right? The thing I'm most excited about is that we can build some AI just like the open source software that we use, something that's kind of close to a common good for humanity. Basically, I think sometimes we're annoyed at the library we use, but I still kind of see them as a common good for everyone. Like everyone can use them, everyone can access them. If there's a bug you're annoyed about, you can fix it. I think it's a beautiful thing that software brought to humanity, and that would be very nice to see AI like this. But then there's a lot of other questions. If you want to dive in this, that's a lot of the things we do at Hugging Face, which is try to think about all these questions and this problem. So that's the very big picture, but I want to dive a bit more in like practical thing today. And this is basically what we're going to talk about. It's six steps, but basically they will go quite fast. I'll talk about the hub of Hugging Face, if you don't know about it. I'll talk about the challenges about inference and training, demos, and then we'll talk about research. So model and data. Why did we build Hugging Face? Well, we built it because we think it's very nice if we share all these artifacts. And the specificity of this new revolution, of this software 2.0, is that it's not only about code. So there are code base, but there is a lot of other artifacts that we didn't use to have before. And one of them is models. Model has usually quite heavy, data focus files. And they can be difficult to host, they can be difficult to share, so that's why we build it. Datasets are something that are slightly more common, I would say. That's why PyData is called PyData. And something new that we're also hosting and sharing on the Hugging Face Hub are spaces, which is a kind of a demo, basically. The idea is if you have a model, it's nice. If you can interact with it very easily, it's even better. And that's actually what we see in practice. So here I show you the numbers on the hub. They're actually slightly old because it's really growing exponentially. This was over the first 6 months of the year. We get 3 times more models hosted on the hub, like maybe 5 times more data sets, and the spaces, it's almost 5 times. So spaces and demo are growing incredibly, and that's kind of linked to the fact that a lot of people now using this model are not anymore software engineer, but they're kind of anyone actually. The Model Hub is a place basically where you can share your model, your data set, your demo. We try to push a lot for best practices. We think a good way to have what I was saying like this, common good for humanity is to push for good practices, which are, in our case, like nice versioning, like saving gated access, maybe controlling how you want to diffuse your model, maybe better documentation around, what did you put in your model, what type of data, and all these things. And our idea is, if you have a nice place for that, if you try to push people in doing that, they actually will want to do that and have a nice way to share the model with like ethical, responsible practices, basically. That's also why we have a community discussion pages. Now, let's say you've chosen, you find your model, and you want to try it. You need to use it in inference. There's a couple of big challenges with regard to like how we did software before, and they're related to what I was saying, which is these models are huge, usually. They're also very hard to evaluate. Having good benchmark, is very tricky, and I think we're still like learning a lot on this. You usually want to tailor them for your use case, but how do you do that, right? You can't just change lines of code. So there's a couple of like things that are very difficult to do. And so we've started to dive in this with what we like to do, which is a combination of a set of open source library, focusing on some problems. So one problem is, for instance, they are too big. Okay, let's quantize them. Instead of having them in 32 bytes, let's have them in 4 bytes or 8 bytes. That's the library bytes and bytes, bits and bytes. And that basically lets you run huge model now on your laptop, almost. You can run, that's really crazy. And the future I see is a future where this model will actually be, just running on any type of consumer hardware. It can be difficult to replicate them or to make them run with batch inference fast. And so we have a set of library, accelerate, and text generation inference that are there to solve this type of problems. Text generation inference, in particular, is a library I like a lot, in part because it's coded in Rust behind, and it's kind of nice, but also because it implements all the good practices that you will want. Usually, when you use this model, you want to deploy them on several GPU, you want to be able to stream your token at them, and not to have to do some complex batching, and basically has all these things in it. So it's a very nice one. Now, let's say you want to adapt your model to your use case, okay? You've find your nice model, you know how to use it, but now it's not exactly what you would like to do. You would like to generate poem about, the shipyard that are now reconverted in conference centers, and Llama model does not really know how to do that. It can be tricky, because basically if you just go for the simple, training, activity models are really huge. So for instance, right now, while I'm talking, I just started a run on fine-tuning this very large Falcon model. And I need 64 GPU, for instance. And that's very small, actually. In the best case, I would like to have 128 GPU to train it. So that's a lot of money. That's a lot of GPU. And so what we've developed recently is also a new library, again, to solve this, which is called PEFT. And the idea here is that you don't need to fine-tune all the model. You can add just a little bit slight, tiny layers of parameters that you will adapt. And you train just these models, just these tiny layers. It's called LoRa or PEFT. And with these things, you can actually fine-tune like a huge model like the 65B Llama one, the largest one, on just a single GPU. So that's also what I was saying. This is coming to like consumer hardware. This is also one of the techniques that make this possible. If you combine that with quantization, like a set of things, you actually now can do a lot with these very large models. Just one example, Whisper, right, is this model that lets you transcribe audio in text. It's quite a large model, but with LoRa, you just fine-tune 1% of the parameter if you want to adapt it to your use case. And it can just work on an 8 GB GPU, which is really small, actually. These are other examples. You can use this stable diffusion, this model, right, that take text and generate image. You can add adapters, and here you fine-tune it to kind of learn some type of concepts, if you want, in the adapters, like the concept of a dog or a toy. And then you can reuse and share, and that's kind of a funny new thing where you actually reuse. It's a little bit like a piece of code. You will share your adapter, which is just a matrix, but basically there is some functionality encoded in it. There's a lot of like new use cases that we're starting to think about, which are very interesting. And here with like LoRa, we see the community, a lot of people training adapters and sharing them, which is very funny. Okay, now let's say you've selected your model, you've deployed it, you've adapted it, and you want to have other people use it. You want to showcase it. Here, you will want to spin up a space on Hugging Face. Why? Well, well, also I do that because that's Hugging Face, so I like to use my own tools at dog fooding, but it's also a very nice thing, actually. Gradio is very easy to spin up. And the idea is, a lot of the time, this model, they have predefined type of inputs, predefined type of outputs, and we know, what they expect. They expect text, the output text, for instance. So we can just plug like pretty pre-made, interface to the input, to the output, and actually this can be very easy to make a model in an interactive setting. So that's, I think, one of the reasons we've seen a huge growth. There was a lot of virality last year when we started to have spaces, in particular around image, text to image, right? On the right was DALL-E Mini. I don't know if you remember, for last summer, it became viral. It was like just made by one guy, Boris, in Texas, just training a DALL-E Mini, and it was able to generate so funny images that became really huge. And recently, in the past few months, there was the Stable Diffusion, various models that they trained that also became really huge. Now, typically, as I was telling you, making a Gradio interface and basically building a Gradio space to interact with your model is just like 3 lines. That's super, super quick to do. You just explain basically what type of input, what type of output. If you want, you can organize that a bit on the page. If you don't want, you don't need to. And then you run it. And what we do at Hugging Face is basically we give you free compute for that. It's a little secret, actually, is that you can use spaces to do many things. So I use them to do pretty much everything when I want to have people interacted with them. And something that was also very viral around spaces this summer was leaderboard. Because one of the big problems when you start to have, we have now 1 million repositories on the hub, is how do you find the model that you want to use, right? How do you know? And so it's related to the difficulty to evaluate this model. It's also very hard to evaluate them. And so we've studied a little bit to make a small leaderboard on that. Actually, for our internal use case, if you look at the organization there, Hugging Face H4 is our internal research team studying RLHF. And they just made this small space, and it became viral and huge. And so I think the idea now for us is to start to build this and to maybe make more leaderboards, maybe make more evaluation of all the models in the hub, because there is clearly a lot of people who would like to know more about metrics and have more metrics on this model. So that's just the beginning. Right now we have 4 benchmarks, but just this week we were thinking about extending it to 7 and trying to cover more and more of the capabilities of the model. Now I want to talk very briefly about open research, because then I'll be a bit longer, right? I'll just go over to say that in addition to the software that we do, we like to organize very large research projects, and I just show you 2 of them. One was kind of maybe a few years ago now, 3 years ago, was Big Science. And here the idea was, okay, all these models are usually trained with very small team in just one company. That's a bit boring. What about trying to train all together, a bit like SETI at home? We're all looking for aliens. Maybe we found 2 of them in Mexico yesterday, I think. But yeah, we're all looking for aliens. Maybe we could also train models together. And so we say, okay, we're going to find a way to get some compute. And then we just invite everyone to come train a model. So we end up being like 1,000 researchers, including actually some of you. Julien was there. Maybe Guilherme, Alessandro, that was before, maybe, yeah. And we trained one model, Bloom. That was the first multilingual model that came just after GPT-3. So that's kind of old now, I would say. But it was a very nice model. It was the first one that covers so many languages. And it's actually still very interesting. There was this study published this summer by Stanford, which was taking all the new regulation that are coming in AI. There is one big regulation in Europe that is being discussed. There is one big regulation in the US that are being discussed. And people talk a lot about, okay, open source, like right of data access and how we should regulate that. And when you take all the proposals that are in Europe today, the model that we made, in this kind of community way, was by far the one that checked the most boxes in the regulation. I would dare to say that's probably the only one that would have been accepted today as a model. And the other one are basically ChatGPT and a bunch of models. They are not all closed source. Llama is also open source, GPT-NeoX. But that's very interesting, I think, as a way to think about these questions. Inspired by big science, that was very, very nice, but also slightly too big, to be honest. 1,000 researchers, 1,000 people training one model is a lot. We've started a second project called Big Code, with actually people here. So Big Code is also a fairly large project now with 500 participants, and is mostly being led by Hugging Face, 2 people, and 2 people here in Amsterdam, Harm from ServiceNow, who are also co-leading it with us. And it followed the recipe of big science with some learnings. So first created a data set called the stack, and we tried to focus on something a bit more narrow, which is code generation models. So like think about Copilot, this type of thing. They're very interesting. They have the same problem as GPT-3 at the time. They're all closed source, they're all private. We have no idea how they're trained. And so the idea was here again, let's try to do something in the open. Let's aim to make a nice code completion model and to make it open, transparent. So we started by making a data set that's already been used actually a lot. And then we trained a model just before the summer called StarCoder. We thought a little bit about what people want. They want models that go fast, that are small, that are very good, that have long context. Well, they want everything, so we tried to put everything. It kind of succeeded, so we had that was in May that we released the models. That was the best open source model on a set of evaluation. And I think it was the very first try at this. Now we're trying to train the second one, just as I'm talking. We're very excited about this as well. And you can see the power of making something open source is that the data set and the model that were shared, they've already been using countless things, and it was just released in May. So May, that's like 4 months ago. We already have like at least three, but maybe more. If you saw yesterday, there was a model called Phi 1.5 by Microsoft, super interesting. It's also trained on the stack in part. So like all the things you release like this, they create a huge ecosystem of people reusing them, fine-tuning model and everything. So that's super interesting to do this type of catalyzation. And now I'll let Julien continue with a focus on data.
Yes. Hi, everyone. So for the remaining of the presentation, I'm going to talk about some work we did in the scope of the Falcon models, along with Guilherme and Alessandro, and some other members of the team as well who are not here today. And essentially, this work is about finding data at scale for large language model. So you've probably heard that large language models have quite an appetite for data and absolutely tremendous quantities. And early on, when we started the Falcon project, like a year ago about that, a year and a half, we essentially realized that the amount of data we would need would be like tremendous, like trillions of tokens, so trillions of words, essentially. And this is kind of relating a bit like the story of us going through different ideas to fulfill that needs. So one of the key ideas that you find in classic large language model literature is that your data set is made of 2 things. So a good part of it is made of web data. The idea is that you need so much data that at some point you need some bulk data that you can get in lots. And the rest is made of like high quality corpora that you are selecting. So this might be books or like technical papers or that kind of things. And if you go through an history of large language models, for GPT-3, they had about 300 billion tokens. If you want to convert in words, you can more or less divide by 1.5 or 2. It depends a bit on the tokenizer. And for GPT-3, for instance, you had about 40% of the data that was coming from what we call curated sources. So once again, these books, technical papers, that kind of thing. Then you had this open source, open data set called the Pile, which was kind of a reproduction of the GPT-3 data that was made by a collective called Letter AI, and which has been used massively in the past few years in a lot of open LLMs. And the Pile, went up to 80% curation. And you have other like state-of-the-art model, from DeepMind, from Google, who essentially had a lot of curated data once again, kind of kept that fraction very high. The difficulty is that getting that curated data is very hard. Each individual sources, each like source of a technical paper or of a book requires you to do manual work, to get it. And the pipeline that you build, to get, for instance, paper from archive, maybe you can reuse some part to get papers from PubMed, but only part of it. So you end up doing a lot of duplicate work, and this is not super scalable. And as like the needs of like large language model training are growing, into trillions and trillions of tokens, this becomes very challenging to accommodate. But the caveat is that you will be like, oh, why don't just go with web data, like full web data? After all, if we already put a fraction of it, why not do that? So here I'm putting some results actually from Big Science, which Tom was talking just about data quality and the impact it has on the performance of the model. And one thing that's very interesting to see is this idea that first, the model from OpenAI, when you evaluate them through the API, actually outperforms significantly even models trained on the Pi, which was supposed to be kind of inspired by the data of OpenAI. So open source reproduction had failed at making essentially data of the same caliber than the one OpenAI was training on at the time. And these numbers, you see it's a difference of 2%. This is actually very significant. I come to this on the next one, but essentially a difference of 2% can account for like a change in scale, how much compute you are putting into your model of like 2 or 3x. So imagine instead of spending, instead of doubling or tripling your GPU budget, you could simply improve your data processing. And obviously, data processing is much, much cheaper than training models. For training the models, you are going to put thousands of GPUs together. GPU compute is much, much more expensive than CPU compute. In fact, in the data pipelines we have developed, we have run on CPU cluster with like 10,000 or 20,000 cores, but that is still a fraction of the cost of running, on the large GPU cluster. So essentially, data is a multiplier of your efforts. You can do a lot of efforts on this. That downstream will save you compute and allow you to be more efficient in your model. And this really highlights the issue with quality. And that issue with quality, people have been linking it to this idea of curated data, essentially. They have been thinking, oh, and it's kind of like, I think it would be the a priori idea that we would all have in this room of like, maybe if I curate the data, if I put sources, like probably a technical paper from archive is bringing more value to the model than just some random web page that I've crawled. And so people were strongly believing that, if we want to scale the data, we also have to scale the curated sources. But this is where it kind of all breaks down. Historically speaking, if you look at GPT-3, people like OpenAI train a 175 billion parameter model on about 300 billion tokens, so about 100, 200 billion words. But actually, if you are looking at like modern practices in models, we have tend to keep the model the same size, but train them for longer. And the main reason this is because you want to serve as small of a model as possible. Because the larger the model you are serving, the more expensive it is to serve. And then your ops people are going against you and telling you, why is it so big? This is a pain to deal with. So people instead, to kind of decouple the compute that you are spending in training and in inference, you train for longer. And then you have a model at the end of the same size, so easier to serve, a smaller one, than the larger model. And if you look at modern practices, you would have to train such a model on 3.5 trillion tokens, which is a tremendous amount of data. And well, this is the specs for the training of Falcon 180B. It's a bit more parameters. It's 180 billion parameters on 3.5 trillion tokens of data. So the question becomes, where do you find that much data? Because this is an impressively large amount. Actually, if you look even at the literature for large language model, in papers, there is no data set that was reported until a month ago that was this big. Like the largest one were reported like a trillion and a half, then Llama 2 trillion, and then what we did actually refine web in total, the full data set we got is about 5 trillion. So this is like a really unique scale. When we stared at this a year ago, this was a really frightening scale. And essentially you have two approaches. The first approach is kind of the naive approach, which people in deep learning have really enjoyed in the past, which is simply upsampling. Just repeat the data, repeat the sources. Most LLMs already do this. They upsample their high-quality sources by 1 or 3 times. The problem for us is that if we do this on like common datasets, we will have to upsample by 10x. And so this will lead to some problem down the line. What's nice about upsampling, is like, kind of we think some of the corpora high quality that we can use, and probably, and this is more of a technical remark, but maybe you can sustain multiple epochs. On LLMs, there is some results for this. However, the issue is that data duplication and memorizations are very scary at scale. Essentially, the larger the model, the more it will have a tendency to memorize. And memorization of the data sample obviously is an issue for downstream use, but also is an issue in terms just of the performance of the model. Essentially, it diminishes quite a bit the performance of the model. The model kind of chooses to memorize at the expense of generalizing, as a very broad idea. This is actually a bit more complex, but yeah. And when we did this now, there is work that shows that probably doing 2 to 4 epochs, so 2 to 4 repetition is fine. When we did this work wasn't there yet, so we essentially were quite scared by this. What you could do instead is scale web data. So we are already using a lot of web data in our large language models. If you look at Common Crawl, so Common Crawl is this is an open initiative from a foundation that crawls the web and make it available to everyone. Like doing crawling at web scale is very expensive. Why duplicate efforts? So this foundation essentially do it for most of the community, and then you can just download it and use it. There is about 100 to 150 trillion tokens in Common Crawl, so this is plenty enough on paper. What's nice with scaling web data is that it's very scalable. Before I was telling you curated sources, it's annoying. You have to walk through each one of them individually. If you get an improvement for web data, you get it for all of it. So it's like a massive leverage that you have. Every hour of engineering that you spend, every line of code that you write has tremendously more leverage because it's going to impact amounts of data that are incredible down the line. There is also, I put this as a maybe, I'm not a lawyer, you should not be taking my advice as legal advice. It's probable that this kind of data has less legal issues. If you go and straight up get books from LibGen, there is a much stronger case against you in court than if you are just crawling web data that is publicly available. And this also leads to this consideration that web data is probably a bit more, it's a bit nicer in this way. However, the big caveat, and I think this is something you can kind of all guess, is that out of the box, web data is absolutely atrocious. If you open a dump from Common Crawl out of the box, the likelihood that you will find something that is incredibly bad is about 70 to 90%. And you will see the exact numbers in the pipeline before. I'm not really making them up. So it's like every bad thing you can imagine. Pornography, gambling, spam content, a lot of machine-generated spam. A lot of the content is there multiple times. And I was just telling you before, we don't want to upsample. But if you end up with the same page or the same text repeated 10,000 times, that's probably not good. So the quality of web data out of the box is really bad. It's like the worst place you can start from. But we are feeling adventurous. And so we decided to go on a web data adventure. And we thought that, OK, let's make web data really good. And we built the tooling for this, and Guilherme is going to present you the pipeline that we built for this called macro data refinement. Yeah.
Okay, so I see someone here has watched Severance by the reaction. So hi, everyone. So we have all this data in Common Crawl, which, as Julien said, is this readily available massive quantity of web data. And it is absolute trash. We have to clean this data. We have to get it ready so we can actually get something usable as a model. So we start with our, our raw Common Crawl data, so which is a lot. And right in the beginning, we have a decision, which is, do we want to use the HTML version of Common Crawl? Because Common Crawl gives this data available in 2 different ways. So you have a version where you have the raw HTML content from websites that I have extracted. And you have a version where they extract the content from this website for you. So the thing we decided early on is that we didn't like this plain text version. So we wanted to roll our own text extraction from HTML. This ended up being the most expensive step in our data processing pipeline. So one good thing we could do is, before doing this, we could actually just look at URL. So this is how we start. We start by filtering the content we have based on the actual URL. We pulled bunch of lists of websites that you should block on things like schools and so on. And we use this word list to start by filtering things like not safe for work content, some gambling content, and so on. So we could, cheaply filter down on things we don't want. And then we take our raw HTML content, and we use a Python library called Traffilatura to extract the text from the content. What do I mean by extract the text? So we don't want menus, we don't want the share this post, related info, all this stuff, right? We just want the actual content of the website. Then obviously we're training English large language model, so we wanted English content, makes sense. So we used a fast text classifier. We basically took each sample, we identified the language of the majority of the content in this sample, and we removed everything that was not English. Out of this, we already filtered down to around like 50% of Common Crawl documents. So luckily for us, English is overrepresented in Common Crawl, which is good. We call this refined web raw in English. We take this data and then we apply some basic filtering. So we have taken the content from the website. Now we want to look at this content and see, is it actually something we want to train our model with? And for this, we took a bunch of heuristics. So these are now quite common. A few of them were discussed in papers by DeMind, mainly when training Gopher. So a few things you can do. You can look at repetitive content within the website. So you have some spam-based like websites that are just trying to spam keywords for search engine optimization, where they just have the same thing over and over. They have a bunch of different paragraphs. So you can try to see, like, you can check ratios of repeated lines, n-grams, words, and so on. You can check the ratio of, for example, lists. Some websites will just see a list of links, so it's just bullet points all over. You can check things like the actual, how much of this content is actually even alphanumeric. You have a bunch of different non-alphanumeric symbols. Probably don't want this sort of thing. And because this is not a perfect process, especially the HTML extraction, sadly, we always ended up with things like, at the end of the sample, you have something like share this, comments, like. So we tried to, this part was a bit labor intensive. We looked at a bunch of things we were keeping. We tried to identify what was there that we could, surgically remove. And we tried to remove all this stuff from the, mostly the footer of content. With this, we have our refined web. So this is our data set. We call it refined web, filtered. So this is about 50% of the previous one. So you see the issue with this is that you think, OK, we have a lot of data. Let's start cutting. But things actually go down quite quickly. So this is something to keep in mind. We then did something that was probably the biggest boost afterwards for model performance. You'll see this when Alessandro tells you about the results, which was deduplication. So as Julien said, deduplication is a big problem for large language models, especially as the size increases. So what we tried to do, and we really went the extra mile here, was we want to make sure that the data we are giving the model is, as to the best of our ability, unique. So you want to make sure that you're not giving the same exact text 50,000 times. And if you just take the web, websites copy data from one place to the other. You have things like, like you have a WordPress plugin that has this, whatever trademark thing that is copied or licensed, that is copied all over the internet. So it is really important. For this, we use two main techniques. So we use minhash. Minhash is a method where you can try to find similar documents. It's a fuzzy duplication method. You basically look at the content, you try to find, make a signature for a document that is where if two documents are similar, their signatures will also be similar. And then you try to identify documents. You make clusters of documents, and we had documents that would be repeated basically like hundreds of thousands of times, which is just a waste. If you're training a model, the GPUs are very expensive. You're just giving it the same thing over and over again. And we removed everything from each of these clusters except for one document in each cluster. We then did a more thorough deduplication method, which is exact substring. So basically here what you do is you remove exact sequences that are repeated in the exact same manner, word for word, in many different places. And here we remove them from all the documents we could find for this sequence. Some previous work, like minhash, is quite common when you're processing data for large language models. Exact substring is not as common. And especially merging these two actually allowed us to scale better, because the scale of data we were operating at is bigger than usual at the time. So we combined these two, and this gave us the final refined web. So about 50% again of refined web filtered. And if we go back to the beginning, it's about 10% of everything in Common Crawl. There was an additional fourth stage that we considered, but we didn't end up doing, which is you can try to use already some machine learning methods to improve the data. So this has been done by other models in the past. You can, for example, have a reference data set such as Wikipedia and try to compare documents to this reference data set, see if something resembles Wikipedia, you say, OK, this is actually good. We opted to not do this. This was a choice. And also, we did not try anything like trying to rules-based methods of, this looks like a conversation. We actually want more conversations. Let's extract this, keep this, and remove other things. So just to be for completion, but the results that Alessandro will tell you about do not include these two methods that we did not use. So here we have a breakdown of everything we got at the end of this entire process. This is a big, scary figure. Just as a note, the gray rectangles are in reference to the previous step. The colorful ones are just in reference to the entire thing. So you can see, as we just filtered URLs, we removed a tiny percentage, about 2.2%. We did our language, our text extraction, our language identification, and we ended up with our English data, which, as we said before, is about 50%. You can see here it's 47.51%. And then we started filtering, right? So we went down and we did our document-wise filtering, where we check if a document is too repetitive, if it, ratios of words or of alphanumeric characters, whatever, don't match what we think they should match. We keep removing documents. We are now 35%. We have removed 24 from the previous stage. We corrected a few lines. This doesn't remove much. And then we have the duplication, which then just takes whatever we have and just gives us half of it. And really, our experience running the duplication at scale was what really made a difference between our dataset and other datasets. So how big the difference was all this? You'll hear from Alessandro now. He'll tell you about the results we got.
Hello, everyone. From Julien, you've heard why we have done it. From Guilherme, you heard how we have done it. And now I will show you how we made sure that actually we did the proper thing. Usually when people do research on pre-training datasets, one of the things that they do the most is to check validation loss on various datasets. We decided to not do that and to check zero-shot evaluation. That's for two reasons. The first one is that validation loss has been shown to be at odds sometimes with the end task. And the second reason is that because we are always training and looking at autoregressive decoder-only transformers, and the most natural setting to evaluate such an architecture is a zero-shot. So we use the EAI harness, and we use an aggregate of tasks with a signal at between 1 and 3 billion parameter. That means that we did these experiments at really low scale, around 1, then we scaled up to 7. But the idea is to have meaningful performance even at that scale, meaning that all the results are far from random baseline, even at low scale. We have a core big science aggregate of tasks, and then we have some other aggregates. For the people who are not familiar with NLP benchmarks, all of them are just like little, small data set where you evaluate how good the model is to do some specific things that can be really easy things, like is it more likely that if I say hello, I'm speaking to a cat or a person, things like that. That can be more sophisticated, but many of them are like really simple as to evaluate the performance of the model. So we trained, obviously, our own model on our own code base on refined web, and we compared to other model of the same size trained on the same amount of tokens, and we compare with the results you can see on the GPT-3 paper for that size. Then we have the same model through their API on the OpenAI website, and then we check with the other models trained by the Big Science Architecture and Scale group. And as I already said, obviously we also trained our model on the pile, also on the pile. So first thing you can see that I find is really interesting is that on the left, you can see 3 models, same architecture, trained on the same amount of tokens on the same dataset, and yet you have different performances. This is just an hint on why sometimes it is hard to evaluate performance, and this is just because they've been trained on different code bases. The architecture is always the transformer, but sometimes there are slight differences, for example, the positional encoding, and obviously sometimes, even if you have trained on the same amount of tokens, maybe they were not the same tokens, there's always a bit of variability on that. And so on the left and on the right, you see the performance of these models on the 2 aggregates we've mentioned. We have external PARM and external Big Science. So this is the performance of GPT-3. One thing that is really important is to understand how impossible was to achieve the same performance for open source model, open source data for a while. Like literally, this performance was so far away that people start thinking that, at OpenAI they had some special recipe that was not available to the rest of the public. And that's why the results I'm going to show you is really important. This is, is the proof that everything you heard about MDR, macro data refinement, actually worked, and is important for a lot of reasons. First reason, it was really important for us. Of course, we did all of the job, and it paid out. But most importantly, you heard how important it is to scale this architecture that we actually able to get enough data. The trend is that most people will keep scaling these models, and using data from curated sources is not the solution. It doesn't scale as fast. And I can tell you that from a person that actually spent quite a lot of time curating specific data that can be archived, can be redded, really takes so much effort to get a small amount of data. At Variance here, we can see that just by refining a snapshot of the web, as messy as it can be, we can reach similar performance to curated data. And this is a result of 1.3 billion parameters. Some of you may argue, that's a really small scale. If you want to check the full experimental setup, there is more experiment on the refined web paper. Short story short, the same result, obviously, they scale up to 7 billion parameters on the paper. We also show an ablation on why, for example, the duplication, as Guilherme said, was really important. And then, obviously, also the results of the 40 and 180B models. I think that was the final slide. So thank you very much. And I guess questions are welcome from everyone.